All right, welcome to session 4 of Electrodynamics. This week it's going to be a lecture by video because I'm traveling away from the country, so I'm very sorry about that, but hopefully this video is going to help you, keep up with the good pace we've been having on the material. So I have a simple plan for today. I just want to talk about separation of variable spherical coordinates again. Last time we just kind of hinted at it, but I thought I'd do a better job explaining stuff today on this. Then in the second hour we'll discuss multipoles. Okay, so let me start again essentially at the end point of last time, which was looking at the Laplacian in spherical coordinates. And let me just make a little comment on this. So first of all, let's just rewrite this this kind of beast. You're not really expected to know this by heart, but still, it would be great if you did. What's the Laplacian? So we have three coordinates, r, theta, phi. Laplacian goes like this: 1 over r squared, and then a derivative with respect to r of r squared times the derivative of our potential v, on which I'm applying the Laplacian, d dr. That's the radial part. Then the theta angle part is 1 over r squared sine theta, and then there's going to be a partial derivative with respect to theta of sine theta dv d theta. Internet keeps disconnecting. Yes, thank you very much. Plus then the phi part, 1 over r squared sine squared theta with the second derivative of v with respect to phi. All this thing has to be equal to 0. Okay. If we are just solving the Laplace equation. Now, just a little note. There are different ways you can write the radial part here. If you actually write it out, you see you need to take a r derivative on these two terms here. If you take the r derivative on this term here, the r squared here cancels with this one. So you just get the second derivative of v with respect to r squared. And then if you just act with the derivative here, you just get like 2r divided by r squared, so just 2 over r with dv dr. Actually, you might prefer to rewrite this in a slightly cleaner form, which is just like 1 over r, the second derivative of just r times v, right? So it's actually your choice. So either you prefer this form here, or you prefer this form here. Actually, my personal preference is for this latter form here. I think it's kind of simpler. It looks more like the Laplacian you're used to. So it's kind of, maybe just cleaner to use this. So I'll do that in the notes today. In the notes that you already have, I use mostly this other form here, but you'll see it's kind of completely equivalent. So it doesn't really matter which one you have. Okay, now our potential is a function of three variables, right? So we've got v as a function of r, theta, and phi. Now, the point of separation of variables is that we're going to assume that we can write these dependencies, if you want, disentangled from each other. So we will assume that we can take a form for this v which separates these dependencies. So I'm going to use a certain function r for the radial part. I'm going to use another function p for the angular part, okay, that I'll write p theta like this. And then I'll use another function that I'll write q for the phi angle dependence. Now, what I can do is just substitute this in my equation, in my Laplace equation here. So what I get is just a kind of big bunch of terms. I'm not going to write all the arguments for all these things, but I will get, so just, v here, but there's only the r dependence, so I get the p times q with now the 1 over r. I'm going to use this form here. And now notice I'm actually shifting to total derivatives because now there's no other dependency here. When I write this r here, the r only depends on little r here, so I can switch to total derivatives here. Okay, so it's the same thing with the other terms. Then I would get like rq divided by this little r squared sine theta, and now d total derivative with respect to theta of sine theta. No, sorry, that's a parenthesis. Sine theta dp of theta d theta, again total derivative. Okay, and then I would have the other term, which would be just r times p divided by r squared sine squared theta d2q d phi squared. And this whole thing would be equal to 0. All right. Now, there's a thing you can note here. Let me note it with a nice fancy little color. So this term here, well, actually, I'm just going a bit ahead of myself here. Let me just actually write another thing. So I can divide out RPQ, right, which is just our RV. Okay. And I can also just multiply by this r squared sine squared theta here. And what I get when I do that is an equation that just looks a little bit different. It's the same equation, but just written more conveniently. R squared sine squared theta, big bracket, 1 over little r times big R, with now the second derivative with respect to r squared of little r times big R, okay, plus 1 over this p function that we had, r squared sine theta d theta of sine theta dp d theta, end of the big bracket. And then I have 1 over q times the second derivative of q with respect to phi. Okay, so what's the deal? What's the deal with this? The point is that if I look carefully at this equation, this term here is the only one with a phi dependence. Okay, so you see where I'm going with this. By the notion of separation of variables, we must have that this 1 over q, q being a function of phi, second derivative of q of phi with respect to phi must be equal to some constant. All right, and then just because everything's like prearranged to get beautiful equations at the end, let me just baptize this constant as minus m squared. Okay, you could put any constant here, and then you just have the same solutions anyway, just expressed in terms of a different variable. But you see the convenient thing about this particular short choice here is that you can immediately solve this equation, right? So this is just second derivative of q with respect to phi is equal to minus m squared times phi. So therefore q of phi is just a phase. You see, so you'd have two possibilities here. You could choose plus or minus I m phi in the exponential. All right, and here you would require that m be in the set of integers, okay, because the value of phi varies between 0 and 2 pi, and you want to have single valuedness of your potential as you go around the full, azimuthal rotation that you can have with this. Okay, so that's the solution, if you want, for the phi dependence that you can have. Okay, now we can go a little bit further, because you see, so if this thing here is equal to minus m squared, which is a constant, then this whole thing here has to be equal to plus m squared, so that we fulfill Laplace's equation here. Okay, so we can just rewrite that out a little bit here. So let me just put the condition that this is equal to plus m squared into another equation. So so looking at the leftovers in Laplace, yeah, it just means this equation here. Then what do I get? I get that I can write that little r over big R with the second derivative with respect to r of little r times big R plus 1, so I'm kind of multiplying out things a little bit, not completely, 1 over p sine theta with d theta of sine theta dp d theta. Okay, and now I've got my my m squared, which reappears, but I've divided out sine squared theta here, right? I've divided out this this guy here. So this whole thing has to be equal to 0. Okay. Now, I mean, this looks a little bit scary, but we can do a bit of progress on this. So, so first of all, we're going to use the method of separation of variables once again, because once again, if I look at the dependencies that I have in here, this is the only place with an R dependence. Okay, so that means that I can actually again put this particular function here to a given constant. So again, by invoking separation of variables, what I get is that I can put, I'm going to put this thing here to a certain constant. Okay, so this this would be equal to some constant that I could name whatever I wanted to. Actually, because ultimately we're going to be dealing with you know, the YLM functions that you'll have learned from before. Let me just put this as L plus 1. Yeah, for the Legendre, it's quite handy to use this constant here. Okay, so this is equal to a constant. Right. So so what can we do with this? Well, you see, so the R is a convenient combination here. So we could define, say, R to be equal to some other function u divided by little r. So what we get is really an equation that says that r squared divided by u, and now the second derivative with respect to r of u is equal to L plus 1. Okay, so you see, this is a kind of very simple second order differential equation, because it can easily be solved by a single homogeneous power of r for u, right? So this is just telling me that if I take a second derivative, I'm going to get some factor here that's going to be the exponent times the exponent minus 1, and that whole thing can be equal to a constant like this. So we're going to try to find a solution. Let's say that u is equal to r to some power alpha. Then what do I get? I get here r to the 2 minus alpha, and now the second derivative of u is just times alpha minus 1. Sorry, that's a minus 1 here. Right? And then r to the power alpha minus 2, because I've taken two derivatives. And then this is equal to L plus 1. Right? But you see this is quite simple, because then it just means that alpha times alpha minus 1 is equal to L times L plus 1. So I've got two cases. I can put this alpha is equal to L plus 1, in which case this thing becomes equal to this, and this becomes to this. Or I can put this alpha equal to minus L. And these are the two solutions that I have for this second order differential equation. Now, that means that the most general solution that I get for this radial part is just a possible combination of these two powers. So the most general solution is that this u of r is equal to some constant that we'll call AL times r to the power L plus 1. But it could also have another part of the solution, which is just some constant BL times r to the minus L. Or in other words, that our function r of r is the same thing, it's just u over r, right? So I can write this as a L r to the power L plus some other constant BL divided by r to the L plus 1. Okay, so this is what we wanted for this this radial part. Full solution is just a combination of two powers. Constants AL and BL will now have to be fixed by the choice of boundary conditions that you have to fulfill. Okay, so that's the kind of complete handling of the radial part. So let's go back to the angular equation. Okay, angular part, I mean the theta dependence. Okay, so what did we have? So we just had this thing here. Okay, so you see, by separation of variables, I've put this equal to L times L plus 1. Okay, so now the equation for P is just this thing here plus L times L plus 1 must equal 0. Okay, so we can just rewrite this cleanly in the following way. So I have 1 over P of theta times sine theta d theta of sine theta dp d theta plus L times L plus 1 minus m squared over sine squared theta. This whole thing has to be equal to 0. Okay. Now, it's never, well, I don't know, maybe some people find it fun. I'm sure you prefer not to work with complicated trigonometric functions. One of the things you can do here is a simple substitution. What you're going to do is you're going to say that the cosine of x, cosine of theta, is going to be a new variable that you'll call x. So what does that mean? Well, in particular, the sine squared is just now going to be 1 minus x squared. If you look at the derivatives, so if you take a derivative with respect to theta, because theta now is a function of x, what you can do is just use the chain rule. So d theta, well, you're going to do d dx, but then just dx d theta. Right, so this is just the normal chain rule that tells you that d theta you can rewrite as minus sine theta d dx. Right, so this is quite handy because again, this sign here, you'll see we can play with it. So looking at this thing, that's what we get, right? So the d theta here we replace by minus sine theta d dx. So what do we get? We get minus 1 over p d dx, right? That's just this of parenthesis. Now I've got d theta p, but d theta is minus sine, so I get a minus sine squared theta with now the d dx of p. Okay, and then I can just like remultiply this one here, and then plus now big bracket L times sorry, I should have done one fewer here. Just clean this up. Okay, so L times L plus 1 minus m squared over 1 minus x squared times p is equal to 0. Okay, so if I just rewrite this a little bit more cleanly using this relationship here, I just get that d dx of sorry, here I've kind of removed the p from here because I've remultiplied it everywhere here. Okay, so d dx of 1 minus x squared times dp dx plus L times L plus 1 minus m squared over 1 minus x squared times p is equal to 0. Okay. Just remember we kind of writing p as a function of theta, right? So p is really a function of theta, which is a function of x. Okay, that's the meaning of this thing. The symbol p here is really p of theta. Okay. Now, the simplest case that we have here is the one where we have this azimuthal symmetry, and the coefficient m is equal to 0. So we then end up with a slightly simpler equation, d dx of 1 minus x squared dp dx plus L times L plus 1 p is equal to 0. Okay, and that is something that you should have encountered before. You should have encountered it in mathematics. You should have encountered it also in quantum mechanics. The idea is that this is the defining differential equation for the Legendre polynomials. Okay, so how do you do solutions for this thing? Well, you actually assume that P is a certain power series. You write essentially equations for the coefficients of this power series, and you try to solve these things by recursion. Okay, so you know, it's not really my job to show you how to do that. There's a lot of literature about this, so let me just like recall for you the most important equations for this. So let me just give you the solution for this equation. So the solution that we have is that this function p of theta that we're looking for is the lth Legendre polynomial for the variable cos theta. Okay. Now, so what are Legendre polynomials? We can write a few of them here. So, P0, let me write them as a variable x here. So this is just one. P1 of x is equal to x. P2 is equal to 1/2 times 3x squared minus 1. Okay, and you can carry on like this. What's the idea of the Legendre polynomials? The Legendre polynomials are the polynomials that are orthogonal with a uniform measure between -1 and 1. Okay, so what do I mean by this? If I look at the, oh, sorry, that's interesting. If I look at, that's very interesting. If I look at the orthogonality relationship for Legendre polynomials, it tells me that if I do an integral between -1 and 1 over x with a uniform measure of the nth order polynomial with the L''th order polynomial, then I get an orthogonality relationship. So the weighing is just 2 over 2L plus 1, with now a Kronecker delta between L and L'. Okay? The index L is just 0 positive integers. Okay? You can write the equivalent. I mean, if we go back to theta notations, really this is like saying that the integral between 0 and pi d theta with now sine theta, because we're just doing the Jacobian, right? X is cos theta, so we just get minus sine, but then -1 to 1, so I integrate 0 to pi, of now PL of cos theta and PL prime of cos theta. That is just what we wrote here, right? This is the same integral, 2L plus 1 delta L prime. Okay, so that's the important orthogonality relationship that you need when you use these Legendre polynomials. And you see what it is. Another thing that you can note, nota bene, if you evaluate any Legendre polynomial at 1, you will get 1. Okay. I guess I'll just quit my Wi-Fi here, just so it stops bothering us. Okay. So, yeah, what else can we say? So these Legendre polynomials, they obey like lots of different types of recursion relations. I'm not going to go through these, but if ever you need any of those for what we need to do, I'll give them to you in separate formulas. Now, the important statement is that we can now write the most general solution okay, to the Laplace equation in the case of azimuthal symmetry. So what is this? Well, it's just plugging together the various equations that we had, right? So we separated variables, but the two separated variable equations have to be solved simultaneously. Therefore, if I choose a certain L here for my solution for the radial part, I must use the same L in the Legendre equation for the angular part. Okay? And because there's essentially a possibility of using any L here, any integer L, then we can write the most general solution as a linear combination of all these possible solutions, because once again the Laplace equation is a linear differential equation, therefore summations of different solutions are still solutions. So what's our general solution? V of r and theta, I remind you, azimuthal symmetry, so there's no phi dependence. What is this? Well, it's the solution, it's the sum over all possible solutions weighed by their own coefficients. So I've got the radial part, which looks like some constant AL times r to the L. It it's got the other bit, the BL divided by R to the L plus 1, okay? And then times the Legendre polynomial PL of cos theta, all right? So that's our most general solution in the case of azimuthal symmetry. So that's cool. And of course, if we don't have azimuthal symmetry, then we need to re-put the solutions to the phi dependence that we dropped here. Okay, but I'm not gonna do that now. I think you probably did similar things to that in quantum mechanics, but for now, I'll just try to keep it simple here. Okay, so that's a very simple thing. Now, maybe what I can do is just talk you through one of the examples that that was in the notes, just to get used to using these things. So it's just let's do an example usage of this. So what are we going to do? We're going to consider a sphere, or a spherical shell with a given surface charge density. So what's this surface charge density? It's a function, sigma 0, that depends on theta. And I'm not telling you what this function is. It's a general function of theta. Okay. Okay, and here the shell has a radius big R here. Okay, just for notations. So what's the way to solve this? Well, we have different things inside and outside the shell. Right. So if we start inside the shell, okay, that is for radii less than the big R, okay, then what must we have? You see, we have to look at our most general solution here, and I'll be interested in the region where the radius can go to 0. Now, if I'm going to take the radius to 0, then I've got problems here, so I should put all the b's to 0. Only these terms are going to be allowed in my expansion. Okay, so the v inside the shell, so for radii less than r, that I'll just denote as this v like lesser, right? So this one here has to be a sum from L is equal to 0 to infinity of only this part of the solution, because this one diverges, so it's not acceptable. So I've got some coefficients, AL. I'll also just give them a little lesser here to distinguish them from the ones outside later. Then PL of cos theta. My solution to the Laplace equation inside the spherical shell has to be of that form. Okay, so this is for well, up to R. So outside, okay, so for R greater than or equal to R, well, once again, we can use our most general solution here, and then look at what we want to do. The radius here is going to go from this big R all the way to infinity. So then this term would give me problems if it was non-zero. So I'm going to need to put all the a's to 0 outside the shell. So therefore the v outside the shell is a linear combination of only these functions here. Okay, so this is summation L is equal to 0 to infinity of now some b outside. Sorry, I forgot to give the R to the L here, right? So PL, let me write it here, but it's there, right? So it's just, and then R to the L plus 1 PL of cos theta. All right. So, what do we have? Well, we've got a bunch of constants here, so we need to fix them. How do we fix them? Well, we need to look at our boundary conditions. So first of all, the potential has to be continuous. So it must be continuous at R. So therefore, we can write a first equation between our coefficients. The equation is simply that the sum L is equal to 0 to infinity of the AL lesser and now the radius to the power L with PL of cos theta. This has to be equal to the summation from L is equal to 0 to infinity of the B greater L times 1 over big R to the L plus 1 with PL of cos theta. All right. Now, the point is that if we look at the angular dependence of the left and right, it only comes through the Legendre polynomials. But the Legendre polynomials are orthogonal polynomials. Therefore, if this equal sign is to be obeyed, every single different L has to have the same coefficients. Okay, so by orthogonality, of the Legendre, what I get is that I can just say that the coefficient B greater L is equal to the lesser coefficient AL with just the appropriate power of the radius. So big R to the 2L plus 1. Okay? So that's our first equation. It sets all the B's if I know the A's. Okay. Now, we've got another boundary condition, of course, because we had in the formulation of the problem that the shell had a surface charge density given by this function sigma 0 of theta. We had seen an equation that told us that the derivative of the potential as we crossed the surface, the derivative perpendicular to the surface was equal to minus the surface charge density divided by epsilon 0. All right, this is what I'm referring to is, let's see if I can find it. Yeah, so here, maybe even earlier. I think it was even here, that one. Yeah, you see, so you just have the normal derivative of the potential is minus the surface charge density over epsilon 0. So we're going to make use of that equation here. What we have is that, okay, so so the discontinuity of the derivative of V at the position of the shell, so at the surface. What does that tell me? It tells me that if I take the derivative of the outer potential with respect to the radius, and I take the derivative of the inner potential with respect to the radial coordinate, that this thing has to be equal to the surface charge density that I have given you, divided by epsilon 0. Okay, so that's our condition. So again, just substituting. Right, I just take the derivative of my functions. What I need to have is that the one above and below and the radial derivative of these things, they have to they have to equate this. Okay, so what is this? If I take the derivative of my solution, my outer solution was this one here. I'm taking a derivative with respect to r. Okay, so I just get that I've got a summation L is equal to 0 to infinity. So the outer one gives me minus L plus 1. B outer L divided by big R to the L plus 2. Okay, and now the inner one was this function here with R to the L. Got a minus sign here, so that's another minus sign. So minus now L, inner L, but then the big R to the power L minus 1. Okay, so this is all summed, yeah? This has to be equal to minus sigma 0 of theta over epsilon 0. Okay, so we can just do the algebra. What that tells me. Sorry, I forgot of course the Legendre polynomial itself. So let me do this little magic of moving this thing. Very handy. Okay. So times PL of cos theta should equal this. All right. So if I now substitute the value of B that I derived here, right? You see the powers are kind of handy for all of this. So what we get is that the summation L is equal to 0 to infinity of now I'll have this one plus this one, yeah, so 2L plus 1 with I'll write everything in terms of the A's, AL, and now big R to the L minus 1, and PL of cos theta is equal to sigma 0 of theta divided by epsilon 0. Okay? So the coefficients now can just be fished back by orthogonality. So the coefficients AL. Oh, let me just yes, I'm back. So we use orthogonality again. So what I'm going to do is I'm going to just multiply by sine theta, integrate from 0 to pi according to the orthogonality relation that I gave you somewhere. This one here, right? I'm going to do that. I've got one of the polynomials here. I'll multiply by another, and then I'll just fish it out. Yeah. So what I get is that if I just multiply this by PL of cos theta and sine theta, and then integrate over theta from 0 to pi, I'm just going to get 2L plus 1 A times R. Okay, so what that means is, you can just write it straight out. A lesser L is just going to be, so there's the epsilon 0 here, that's going to be, well, maybe, the 2L plus 1 here, you see, is going to be absorbed by the 2L plus 1 here. When I do the orthogonality relation, there's a 2 left over. So it gives me 1 over 2 epsilon 0 R to the L minus 1, integral from 0 to pi d theta sine theta of the sigma 0 of theta that I had times the known PL of cos theta. Okay, so provided you've given me the surface charge distribution, I am now in a position to compute these coefficients for all values of L. Knowing those coefficients, I know the potential inside. Knowing the potential inside, I can use this relation to get the potential outside. So the solution to Laplace has been found throughout space. Okay, so it's just a question of like doing some examples with this. Yeah, I mean, there's one simple example in the notes. Do I even bother doing it? I mean, I think you can look at it yourself. It's like better to maybe look at the generic solution. You see here that irrespective of the function that I give you here, I can decompose this function in the basis of the complete basis of the orthogonal Legendre polynomials. Okay, so that's how problems with azimuthal symmetry can be solved. Okay, and I mean I'm pretty convinced that you already knew all of that, but still it's kind of good to do a refresher and maybe go through the details here. Okay, so let me stop here for this session, and then next one is going to be multipoles.